Good morning, dear students. We are going to discuss now a module on forces and their principle of superposition. We will be studying the concept of the force anyway in future course of modules where we talk about Newton's laws. I think many of you are already aware of the Newton's laws and the force. The word force is such a common thing now for any science student, and even for a common man a force means something which is very much linked with motion. Your body has to move, there is a force required for it. And without applying a force, you cannot make a body move. And therefore, the force and motion, they are very, very intricate things which are to be detailedly discussed before going into the actual effects of this force. In mechanics, when we discuss, in fact, in physics, as you see, there are varieties of forces coming up in nature. We classify them here for discussion. We have nuclear forces, electric forces, magnetic forces, mechanical forces, and so on. The force coming due to electrical reasons, force between electrons, force between protons. Similarly, force between nuclear particles within nucleus itself, while they are in nucleus, nuclear forces. Mechanical forces like what we make use of in moving bodies, driving vehicles on the road, and so on. So, the varieties of these forces are always involved with certain principles, because as we had already mentioned earlier in vectors, these are the physical quantities. The forces are physical quantities which have got both magnitude and directions. Therefore, force is a vector quantity. Because it is a vector quantity, the direction and magnitude must be taken into consideration whenever you operate with them. When a body is moving, for example, it may be having a number of forces acting on that, but the body may be having a definite motion in one direction. So that particular motion of the body in that direction is taking place while all forces are acting on that body. So how to account for that? All forces, how they are working there together, how they are superimposed there, so that the body moves in one direction only accordingly, has to be known both in magnitude and direction in the computation here. So our present module is based on that. Let us go into this a bit slowly, one after the other. The first thing that you must know is what are the basic problems that we come across, basic forces which we come across in mechanics. We talk about mechanics here, concentrated on that. When we go into electricity and magnetism, those forces also can be taken up eventually there. In mechanical context we have, there are forces of varieties. One is what is called as a weight. Generally everybody understands this. Everybody understands that every body has it. A body is having a mass. Because of the mass there is a weight in it. The weight is due to the attraction of the earth on the body. The attractive force on the earth of the earth on the body itself is what is called as weight. Then there is another force called friction. When a body is moving on a surface, the motion is retarded by the friction. You move a disc on a floor, after going some time it stops there. It slows down and stops there. Because there was friction on the floor, it could not infinitely go like that. So this velocity is reduced, speed is reduced. So therefore, friction is one force which comes acting on the body when motion is taking place. Similarly, another force is there which is called as tension in strings. When you try to suspend a body, because the weight of the body is acting vertically downwards, the string will be trying to support that with a tension there. You suspend the body like this with a string there, the weight of the body acts downwards vertically, tension takes place vertically upwards. So both forces are acting on the body now. So this force which comes up in the string because of the suspension there is what is called as tension force. This also is required to be known whenever we are working with mechanics, because you will see in future in modules the problems with tension also will be involved. Then we have another important force also, what is known as normal reaction. This is another force that you must understand. What is normal reaction? Normal reaction means whenever you keep a body on a surface, there will be a contact there between the body and the surface. This contact will give rise to a force on the body from the surface perpendicular to the surface, perpendicular to the contact there. This is what is called as normal reaction. So whenever there is a contact for any body, when the body is moving on the ground, suppose friction is there, other forces are there, because of the contact, normal reaction also will be there on the body. So this force also is involved. There may be problems in mechanics when you use all the forces may be combined, or maybe number of forces are acting there. Friction is there, tension is there, normal reaction is there, all are there, and the body is still moving in one direction. If you want to consolidate the motion of the body in that direction, you must know all these forces are imposed on that, superimposed on that, and you must know how they are to be accounted for, calculated there. That is done according to the principle called superposition principle. We shall do that in course of our discussion today in this module. Let us take an example of a body with simple forces acting on that, one acting like that. Another force also is applied on that in the same direction. Say this is F1 and that is F2. Both are acting on the body in the same direction. Then both are trying to move the body, they try to move the body. So the effective force acting on the body, you can easily, by common sense also you can say that it must be equal to F1 plus F2. So both forces are in the same direction. So the effective force will be sum of the two forces there. That's what we told in vectors also earlier. The effective vector in this direction is sum of the two vectors here. And that vector incidentally here is force. Now you can see, instead of having two forces like this, you can do the same thing by a single force of this value. Suppose F1 plus F2 is written as single force F there. We could replace this two forces with only one force, and that's value F, which is having the same effect of the two forces which had applied earlier. That means you have replaced F in place of F1 and F2. Together they amount for the same force. They will be having the same effect as that force. Then we say this F is the resultant of, we call it as resultant of F1 and F2, we say. This happens generally. I gave a simple example of two forces acting in the same direction. Even if number of forces are acting on the body, all the forces together will give only one effect ultimately, making the body move in one direction, suppose. So the resultant force that is responsible for the movement of the body is what you are supposed to account for. That's why we must understand what is meant by the resultant force. Resultant force is that force which can be used for replacing all the forces which are giving the same effect as the single force here now. So all the forces will have together, put together, they will have the same effect as single force. We take the example like this and try to follow up. One example I have seen just now. We can take another example. Suppose the two forces are acting in opposite directions. There is one force here F1, another force is here F2. Say F1 is less than F2. There is a greater force than that. Both are applied here on the body. Then what happens? This will dominate over that force because they are in the opposite directions. So what will be the effect? The body will try to move this way, not that way. So the body moves this under the action of a force which is the difference of F2 and F1. So F2 minus F1 will be the effective force here, which will be in this direction. towards left, like this. Then we call this F as the resultant of these two forces. So in the case of the forces acting along the same line, in the same direction or in the opposite direction, we can find resultant like this. If they are in the same direction, F1 plus F2 will be equal to F. If they are in the opposite directions, it is F2 minus F1 in this case, or it can be F1 minus F2 also if F1 is greater than F2. Here F2 is greater than F1 we have taken. Suppose F1 is greater, then you have to take the equation like this. Ultimately saying that the direction of this resultant force will be in the direction of this difference. Here F1 is positive and that is greater, therefore it is F1 minus F2. Here F1 is lesser, F2 is greater, therefore F2 minus F1 is the resultant force, it will be in the direction of the F2, that is towards the left here. So like that, in the same direction or in the opposite direction, it is easy to follow up. Then, suppose they are not in the same direction or opposite direction, they act in different directions, which are neither same nor opposite. Then what we do? Suppose there is a body here, and there are two forces acting on this body. Or sometimes we will say a force, let us say first one case of this one, force is acting in the direction. Then we go to two forces. The body is moving now in this direction. Then effective force is in this direction, therefore the body may be moving in this direction. We'll come to this later anyway, we'll do it again. Please start repeating this. Suppose two forces are acting in two different directions. One like this and one like this. There is a point O. There is a particle O, a body like that. One force acting in this direction, one force acting in the directions. At an angle here, theta involved. Then, how to understand this effective force? What will superposition principle say? In the earlier case, we told about F1 plus F2, that simply. That is what vector rules say. What is meant by this rule? It means F1 will act on its own, F2 also will act on its own as if it is acting there independently, but the effect will be both of them put together. The body will have a different effect. That the total different effect what is coming on the body is because of the combined effect of the two forces. We call that as resultant force. Suppose two forces act on a body like this now. Like for example, there is a boat here pulled by two ropes from either direction on a river there. So the boat will move in this direction, you know. It will not move in this direction, it won't move in this direction. This will try to pull this way, that will try to pull that way. Both will do it. But the force, the body will move in this direction, boat will move in this direction. This force is what is called a resultant force of these two now. Effective force is that, resultant force is that. So how to get the resultant force? Rule is the same again. R is equal to F1 plus F2, vectorially. What is meant by getting that effect vectorially here? See in the figure here. Vectorially means at the end of F1 you must write F2. That is F2. Then draw the triangle. That gives you F1 plus F2. So therefore this becomes equal to R. The resultant force will be like that. So this is the way of combining the forces. This is the principle of superposition in the case of two forces. Earlier we have shown the two forces in the same direction, now it is in different directions here. So what will be the direction of this force and what will be the magnitude of this force, resultant force R here, you have to put from the vectorial equation and put in the triangle there. Geometrically you must calculate it. But it is a matter of convenience if you can know the value of resultant force directly from the values of F1 and F2. Say. Naturally you don't have to go every time for the triangle. If you know F1 and F2 and the angle between them, you can know the resultant force acting there. It will be much convenient. We have a method like that. That method I am going to tell you now here. See here. The same thing. I will draw here like this. This is F2. This is F1. Angle theta. We complete the parallelogram here. Draw a line parallel to this one, draw a line parallel to this one, and complete the parallelogram like that. Then, this diagonal of the parallelogram, drawn from the same point, gives you the resultant. This is not something different from that. I am putting the same thing in a different way, that's all, in a different words here. The triangle what you have drawn there is now put on the parallelogram here. This is parallelogram. Suppose we draw OA representing F1, OB representing F2, and OC representing R. OA, F1, OB, F2, OC, R. The law goes like that. This is what is known as the parallelogram law. Parallelogram law. It tells that if there are two forces acting at a point, you can find the magnitude and resultant of that force, which is resultant of these two, from the same point drawn as the diagonal of the parallelogram on which these two forces are represented as adjacent sides. That means, if you draw the length OA proportional to the force F1, similarly OB to F2, then R in both magnitude and direction will represent the effect of the two forces together as resultant there. That means, if you can work out this one, this can be shown. This angle from the geometry, you know very simply, this can be written as OC square. If you take, you got obtuse angle triangle principle in geometry. This is obtuse angle here, opposite side there. So the theorem says that the diagonal square is equal to OA square plus OB square plus 2 OA OB into cos theta, the angle between them. This is what the obtuse angle triangle theorem in geometry says. You can apply the geometry here now, because whenever two forces are acting like that, the forces are always represented on the parallel sides. If this is F2 here, this also will be equal to F2. So this triangle OAC is just as is bearing F1 and F2 like what F1 and F2 are here. So the value of the magnitude of the force F2 is as good as AC. AC will be equal to OB equal to F2 in magnitude, you can see. Similarly, OA is equal to BC is equal to F1. Therefore, this OC is equal to R in magnitude. Direction is given by the diagonal there, drawn from the same point. If you want to give direction, that can be given along with one force there to take angle as alpha. We can give the value of alpha, then you have given the direction there at all. Then C. That means, if you want to get the value of the R, the resultant, as shown here, it must be square root of OA square. That means F1 square plus F2 square plus 2 F1 into F2 cos theta. This equation will give you directly the value of the magnitude of the force, resultant force of F1 and F2, which are acting at a point. So this geometrical representation of the forces on the parallelogram will yield this result. So you can remember the result for working out the effective resultant force there. What is the angle at which it is acting? Suppose you want to find out that. It can also be shown that tan alpha, what means alpha is the angle made by resultant force with the first force F1 here, OA. You must remember those things. That is given by F2 sin theta by F1 plus F2 cos theta. You can show this also geometrically on the same lines there. This can be done. So if you want, you can just make a construction here, just extend this a little there, this also will be theta, then find out from that tan this also will be, you can find out what will be the value of tan alpha from this right angle triangle here. You can prove it. Well, you can remember the result. If you can remember this, you can directly apply now. Let us see the application of this, whether it is correct or not. In a certain case, we will see. I mean to say that this result is more convenient for working analytically, but it is derived from the same basic principles of vectors what is said for the superposition for the forces there. We are trying to do that only. So suppose now, if theta is equal to 0 degrees, suppose. This means the F1 and F2 are in the same direction. Both are in the same direction. What is the answer what you got for that? F1 is equal to F1 plus F2. That means the magnitude of F should be equal to F1 plus F2. We got it from the geometry earlier. Let us apply it here and see. R will be equal to, we call this resultant here, we are calling it as R here, that's all the difference. So resultant here is given by F1 square plus F2 square plus 2 F1 F2 cos 0. Cos 0 is 1. That means this is F1 plus F2 whole square under root. So it must be equal to F1 plus F2. So clearly the resultant is given by the parallelogram law is carrying with the two forces if they are acting in the same direction, that is when theta is equal to 0. Similarly, you can see if theta is equal to 180 degrees, suppose, say. Then what happens? You will get the same equation, R, same F1 square, F2 square, plus 2 F1 F2, instead of cos 0, now we put cos pi. You know, cos pi gives you minus 1. This is minus 1. That means you will get a minus here. Therefore, R becomes equal to F1 minus F2 whole square under root. So it is F1 minus F2. You can also interpret as F2 minus F1. F1 minus F2 whole square or F2 minus F1 whole square, both are same. So therefore, either this can be the answer or that can be the answer. Depends upon which is greater. If F1 is greater, you take this one. If F2 is greater, take this equation. So like that, the resultant of the two forces can be applied even when they are acting in the opposite directions. Pi means 180 degrees means opposite directions. This is F1, this is F2. In that case, we can apply a parallelogram law like this. It gives the same result. So this shows that our law is giving a very accurate result for any angle also in general. We can take up one more case to show that. Suppose we have theta is equal to 90 degrees. Then resultant, how do you find? Apply the same equation, F1 square, F2 square, plus 2 F1 F2 cos 90. Cos 90 is 0. That means the entire thing becomes 0. Then what are you left with? R is equal to square root of F1 square plus F2 square. F1 square plus F2 square under root. You can see this, the two forces are acting at right angles to each other. F1, F2, then the parallelogram becomes rectangle now. That will be resultant force R. What will be the angle now here? You can see this is F2, this is F1. So according to the rule what I said, tan alpha must be equal to F2 sine angle between them, that is 90 here, F1 plus F2 cos 90. That is the rule. Now see here, sin 90 is 1, so it is F2, F1 here, this is 0, therefore the entire thing is 0 again. So you get tan alpha is equal to F2 by F1. That is what is expected in the geometry also. When there are triangles here, this will be equal to that. So tan alpha is F2 by F1 directly. That is what is given even in the case of the parallelogram law result. So we can apply the result from the parallelogram law for solving these problems. Now suppose there are more than two forces acting at the point. Then how do we go about it? That is the next thing to be known. As far as two forces concerned, this method is simple, easy to follow. We can understand that. Suppose there are three forces now. Then there is like that, suppose. Then what will you do? How do you find the forces? F1 is here, F2 is here, F3 is here. How do you find resultant now? Our rule goes for two of them only. So you can find resultant of these two forces, first say F1 and F2, by applying the parallelogram law like that. By knowing the angle there, you will get one resultant. Then this force and this force, you must draw a resultant for both of them, and that gives you the final resultant here. So like that, for every two force you must go on applying parallelogram law and then ultimately resolve them. That becomes a more complicated procedure. We have a simpler procedure than that. In vectors we had also seen one method, one way of dividing a vector. That means you can have components for a vector. Like, very simply like what we said. Now, if two forces, two vectors are like this, two forces are there, F1 and F2 are triangles to each other, the parallelogram law tells that there is a resultant coming up here. We know that. So this is F1, that is F2, that is resultant there. Then this will be F2 here. If you know this angle as alpha, we told you how to write this angle alpha. Tan alpha is equal to F2 by F1, one thing we said. Okay. Now you see the other way of putting it also. We also told the components of a vector. We can resolve a vector into two components. Components means the parts of the vector. When you combine these two forces, you are getting that means you can also divide this force into two parts like this. Then these two parts will become two components. We have shown the rectangular components for simplicity there. So here also you can see that. What is F1 now in the context of the components here? F1 is nothing but R cos alpha in magnitude. Similarly, F2 is R sin alpha. So you can resolve the vector in two components like this. Then you can represent this R, the resultant of them, as R cos alpha into I plus R sin alpha into J. We have told this notation, where I is the x component, unit vector in the x direction, J is the unit vector in the y direction. So this is y direction, this is x direction suppose. We can write this also as Rxi plus Ryj. That is what the notation of representing a vector in the form of its components. So when you can apply this concept of the components together with what we have just now discussed, we can always represent any number of forces simultaneously superimposed into one single resultant there. That method is possible to be done. Let us see how it is done. I will show this here on this only. What I have done here, I will show in that method. Suppose there are two forces acting. We have shown the parallelogram law for that. In one way we combined with the parallelogram law. Here we are using the component method. We will do. I will put it general example. Let us take two forces like this. One like this, one like this. F1, F2. The parallelogram law says the resultant will be somewhere here. You have to think of the parallelogram there and so on. Another method is think of the components of the vector now. Draw from the point x-axis and y-axis. This is y direction, this is x direction, this is force F2, force F1. Let us say the angle made by F1 is alpha here, and this is beta made by the second one. Angle is this is alpha, that is beta, suppose. Now you can resolve the F into two x components, x component, y component. Resolving F1, what will you get? We will get x component, that is F1 cos alpha, and F2 Fy, that is F1 sin alpha. Similarly, we resolve F2, suppose. Then we will get the x component of the second vector, F2x, that is F2 cos beta. The angle made by that vector is beta with x-axis. Similarly, the y component F2y is F2 sin beta. That means the force F1 is given as F1x I plus F1y j. Similarly, F2 is given as F2x I plus F2y j. Now suppose you want to combine F1 and F2, get the resultant there. In combining these two, we know the vector rule that F1 plus F2 happens to be resultant of these two. How do you join them? Put them like this here. F1, x, I components are there, so you can put them together. F2x, both are in the same direction. F1x is in the same direction, F2x also in the same direction. So they simply get added up, components are added up there. So you will get this as F1 x plus F2x I. Similarly, F1y plus F2y, y components, they are in the j direction. So this becomes the sum of F1 and F2 from the knowledge of vectors. We have already seen this earlier, so I have put it directly from that. Therefore, the x component of the resultant is given by square root of F1x square plus F2x square under root. This is the x component of R is F1x plus F2x. Similarly, y component is F1y plus F2y. Suppose now you want to find out the magnitude of the resultant vector R, resultant force R. That is square root of this Rx square plus Ry square. This is Rx, this is Ry. You will get from that. Once you know that, you want to find out direction at which it is happening. Suppose the resultant comes somewhere like this. You want to find that direction here. With the x-axis you can find the direction. Suppose that angle I take it as theta for you to show here. Then according to the principle there of the vectors what you have seen, the tan theta, if you draw this R like this, tan theta will be, you will get y component value by x component value. This is what we have shown. This is the effective x component, this will be the effective y component. So Ry by Rx gives you the tangent of the angle at which the resultant forces happen. They are taking place there. So we can now find out this way easier. So when you have got forces like this acting at a point, that means on a body simultaneously superimposed, you can always get them, the resultant of them, by easily putting them in the component form. When you put in the component form, not only that you can get the magnitudes, you can get direction also, you can get each component of magnitude also separately along x direction, y direction and all that. Suppose you have got 3 dimensions, then you can also extend these 3 dimensions also further. J component is there, then k component also is there, suppose. You can extend it further easily. We can also extend this to any number of forces now. The parallelogram law of forces was limited to 2 forces only. If you get more than 2 forces, naturally you will have to go step by step, 2 each time. I told you it will be more complicated. If you go in the component form, any number of forces may be there, put them all in components, it becomes easier. We show an example here. Suppose there are forces like this. Say this is F1, this is F2, this is F3, this is F4. 4 forces are acting like this. And you are asked to find out resultant of all these forces on a body or a particle like O. So parallelogram law becomes more complicated in application there. So let us go to component form here. What you do is think of x-axis in one direction like that, and y-axis in one direction like that, with the body at the origin. The point where all the forces are acting can be taken as origin there. Now resolve each force in the direction of x and y. Let us say this angle is alpha, then this angle is beta, let us say like that, and rest of the angles we don't require to be known anyway, we will be seeing that. Or also like this. Okay. Like that. The x and y axis, positive side, this is positive side, this is negative side. Okay. Now we have to put these things into component form. Let us put first F1. F1 has 2 components. We are trying to find out resultant of all the forces. Let us say the x component of resultant. I am going directly to answer them very easily. Then add all the x components of the forces. They are simply added like that, just like what you have done in the earlier example. This is in the x direction. X component will be F1. The x component is always given by F cos angle, whatever is the angle there. F1 is in the same direction, angle is 0, therefore it is simply F1 itself. So F1 x component is F1 plus F2 x component is angle is alpha here. What is the x component here? F2 cos alpha. F2 cos alpha is the component there. Then F3 is in this direction, angle there. So it must be F3 cos beta. Then plus F4. F4 is at right angles to x axis now. So it is F4 cos 90. If you simplify this, you will know this is F1 plus F2 cos alpha plus this angle beta is nothing but this is 180 minus beta. That means if you write this way, you will get a 180 minus beta, cos angle will be this side. So the angle, this will become minus now. This will become minus F3 cos beta will come here. Or sorry, I will show this way. Let us take the angle beta here. So it is easy to follow. So instead of showing the angle there, I will show it here. f3 cos beta with x-axis. So if you see like this, the angle is beta. Cos component will be in this direction. That direction is minus direction, negative direction for the x-axis. So the cos component will be with a minus sign here. That plus becomes minus here. If you write like that, you must write 180 minus beta there. Cos 180 minus beta, I will write here. So, if I represent the angle here, it will be convenient, so I put like this. So, 180 minus beta is this angle. So, there will be minus cos beta when it comes here. Plus, this becomes 0 because cos 90 is 0. So, we are left with only 3 components, that is f1 plus f2 cos alpha minus f3 cos beta. That is x component. Coming to y component now, in the same way. Put y components of all the forces together there. The F1 is the force acting along x-axis. The component in the direction will become 0 because F1 sin 0. Because this angle is in the same direction, there is 0. So F1 sin 0. So the y component of the resultant is given by the first y component of first force, that is sin 0. Second force F2, and that is in this direction. This is alpha angle here, so it is F2 sin alpha will be sin component. Then for third one, F3 sin beta, this is in the same direction, positive direction here. This is negative direction, therefore there is no problem. It will be plus only here, it is not minus. And F4 is in the opposite direction, so you must write minus F4 here. So this will become the y component of that. We are writing F4 here because in the same direction. In other words, I can write like this also here as minus F4 sin 90. This sin 90 with the x-axis, sorry. Okay. We can write it as minus F4 sin 90 because this angle is 90 degrees here. So in any way, if you write this into single term, it is F2 sin alpha plus F3 sin beta minus F4 comes here. So like that we have got the x component and y component of the resultant force now. Once you know them, you can find out the sum of them and write like this also in the vector form. That becomes resultant here. That means you can write all this F1 plus F2 cos alpha minus F3 cos beta into I plus F2 sin alpha plus F3 sin beta minus F4 into J. So once you know them, you can find out magnitude and direction like what we said earlier. So the putting in the component form, it becomes very simpler. So numerical examples given in your book on this. If the numerical values you can always attempt and then know how to put them in the superposition principle by component form. Always try to work with the component form, it becomes very easier. Only thing what you have to know is how to choose the axis here. You can choose this axis, x-axis and y-axis any way you like. Accordingly, you will get the answer, but the direction of the resultant will not change. Magnitude will not change. Resultant will be the same. You will be reading with reference to the axis that you have chosen there. For example, in this way, we have taken like this. Suppose you choose the x-axis here. The angle alpha beta will be different there. But so the answers will be different here. But ultimately R will show the same magnitude, same direction only what it is coming now. Even though you take it that way. It is choice of your first choosing the axis, coordinate axis becomes very critical. Once you choose that anyway, it is arbitrary in the beginning. Once you choose it, finished. every answer will come with respect to that axis only what you have chosen there. Now you can attempt the problems given in your module and get to the working of the superposition principle of the forces. Thank you.